These are the notes for section 3.1. You should have a note sheet that goes along with this section. If you didn't get it in class, I posted a link to it on my website, and you can also just do it on regular paper or graph paper, and then copy it down later, or just have it on graph paper. So this is about systems of equations. Our new chapter covers systems of equations. This is something that we covered pretty heavily in the end of 8th grade math, so I'm hoping that a lot of this is pretty familiar to you guys. So what we're going to be doing this chapter is solving something called systems of equations. So a system of equations is when you have two or more equations. And they kind of, if it's a word problem, they have to do it the same situation. Otherwise, we just graph them on the same graph. And what we're going to be doing this chapter is we're going to look for a solution by finding a pair of numbers for which both equations are true. So we want to make it so that both our equations are true, and that pair that works in both equations is our solution. So the first thing we're going to talk about here is how to translate some of these situations into a system of equations. So this first problem says in 2012, there were 92 species of birds in the United States that were considered threatened or endangered. Threatened just means they're not quite endangered yet. The number of species considered threatened was 3 less than 1/4 of the number considered endangered. We need to write a system of equations that models the number of U.S. bird species considered endangered or threatened in 2012. So the first thing I want you guys to do when you're working problems like this is I want you to define your variables. So we have two variables we're talking about here. We have the number of bird species that are threatened and the number of bird species that are endangered. So our first one, just a second, someone's opening my door. Let me go see here. Okay, so our first variable that we have is the number of bird species that are considered threatened. So I'm going to use T to represent the number of bird species that are threatened. And yes, you do have to write this out. Then we have the bird species that are considered endangered, so I'll use an E for the number of bird species that are endangered. Number threatened and number endangered. So I like to start with the one that is, let's start with just the fact that there were 92 species of birds that were threatened or endangered total. So that means the number of threatened plus the number of endangered, they add up to 92. So one of my equations is that T plus E equals 92. That came from that 92 right there, because I know that the number of threatened plus the number endangered must add up to 92, because that was my total. Then they give us another hint here. They said that the number threatened is 3 less than 1/4 of the number endangered. So let's try writing that. Threatened equals 3 less than 1/4 of the endangered. So we need to take 1/4 of the endangered, that's 1/4 times E, and we want 3 less than that, so we need to subtract 3 from that. I think that works out. The number threatened is 3 less than 1/4 the number endangered. That works. So actually, your book does not do this next part, but I'm going to do it. I'm not going to take points off if you don't do it, but if you remember last year, most of the time that whenever you write a system of equations, you do this symbol to show that it's a system of equations. So I think it's just a good practice to get started doing that. That just means, hey, look, these two equations go together. All right, if you can see on your handout, I want you guys to try the next problem here. So here's another word problem. It's very similar. I want you guys to try this one. All right, we're going to do this one together again. So it says Boulder Flatiron's jewelry design purchased 80 beads for a total of $39, excluding tax, to make a necklace. Some of the beads were sterling silver, costing 40 cents each, and the rest were gemstone beads, costing 65 cents each. We're going to translate this to a system of equations. So again, I need to define my variables. The two things I have here are how many sterling silver beads I got and how many gemstone beads. So I don't like to use I don't like to use S in equations because it looks like a 5 sometimes. So I'm going to use X to represent the number of silver beads, the number of sterling silver, and I'm going to use G to represent the number of gemstones. Now notice that I wrote number on each of those. That's really important because I really need to know that you can't just say X equals silver beads because I don't know if it means how many silver beads. I don't know if it means how much they cost. I don't know if it means how beautiful they are. So you need to just tell me exactly what that variable represents. Let's try writing our equations now. So there's a similar thing going on here. They gave us a total. We know she bought 80 beads total. So one of our equations is that the number of silver beads, X, plus the number of gemstone beads, G, must total up to 80. That's our first equation. That's usually their easier one to get, the total. Our second one has to do with the cost. So we know the total cost is 39. The silver ones are 40 cents each, and the gemstones are 65 cents each. So I know that I'm paying 0.4 of a dollar, 40 cents for each silver bead. So I'm going to multiply it. Plus I'm paying 65 cents for each gemstone bead. And when I add up those amounts, it's going to cost $39. So that's my system of equations. Those are the two equations I pulled from that. All right, we're going to go on to the next part of these notes, which is determining whether an answer is a solution. So after we do this, we're going to get to solving these systems on our own. But before we do that, we need to know how to check whether an answer is a solution. So what we're about to do, this is how to check your work later on when we actually solve these systems on our own. So to check whether it's a system, all we're going to do is plug in this X and this y into both of our equations. If it works in both equations, then it is a solution. All right, so what I'm going to do here is I'm going to plug in -4 for x and 7 for y. Okay, if it makes both equations true, so if it works in both equations, then it is a solution. So let's try it here. I've got my first equation is x plus y equals 3. So I'm going to plug in that x and that y. -4 is my x, plus 7, which is my y, equals 3. I just got those from that coordinate they gave me to check. Well, -4 plus 7 is 3. And that works. 3 equals 3. So that works. So it works in the first equation. Let's try the second equation. My second equation is 5x minus y equals -27. So I'm going to plug in my x and my y. 5 times x, so 5 times -4, minus my y, so minus 7, equals -27. Let's see if that's true. 5 times -4 is -20, and I have minus 7. And -20 minus 7 is -27. So that makes my equation true. So it worked in both of those equations, so that means that yes, -47 is a solution to that system. And what that means is that if you graphed both those equations, those graphs would cross at that point. That's what that means, that it's a system. It means that pair of x and y works in both of those equations, and the graphs would cross at that point. That's what it means for something to be a solution to a system. Remember, you can use this to check your answers when we're solving systems. I'm going to have you guys try the next one. I want you guys to determine whether 6 -1 is a solution to this system. You should come in with that done tomorrow. All right, I'm going on to the back of our page now, and we are going to solve systems. The first way we're going to learn to solve these systems is graphically. Before that, I have a joke for you guys. I told you guys I'd put a joke in the next one. So here's my joke. Okay, so there's two guys, and the first guy says to the second guy, "Hey, look, I made a belt out of all of my wristwatches." And the second guy says, "Well, that's a real waste of time." Get it? I thought that was a good one. I laughed when I saw that. All right, so we're going to solve these systems graphically. This is a good method to use if you have two equations that are easy to graph, and if they end up graphing at two integers for your coordinates, basically, which, yeah, you don't know it to begin with, so I'll try to only pretty much give you nice ones for graphing, because if they happen to cross at like 2.5 comma 3. You might not be able to tell if it's 2.5 for your x, so I'll try to only give you nice ones for graphing. So one way to solve a system of equations is to graph both equations and identify any points of intersection. The coordinates of each point of intersection represent a solution of that system. So we're going to solve this system graphically. So your first step that you want to take to solve a system graphically is, well, we want to be able to graph these. So we want to get them both in slope-intercept form. So I'm going to take this first equation right here. It is y minus x equals 1. I want it in slope-intercept form. Remember, that's y equals mx plus b. I want y by itself. So I'm going to add x to each side. So I'm left with y equals x plus 1, or you can write 1x plus 1. Now I'm going to get my other equation in slope-intercept form. So that's y plus x equals 3. Remember, slope-intercept form means get y by itself. So all we need to do on this one is subtract x from each side. And we're left with y equals negative x plus 3, or you can write negative 1x plus 3. So after you get them both in slope-intercept form, your second step is to go ahead and graph them. Remember, when you're graphing equations, you start with your y-intercept. So I'm going to graph this one I have written in blue first. My y-intercept is positive 1, so I make my point on my y-intercept. And then my slope is 1. I could also write that as 1 over 1 to see my rise and run. So I'm going to rise 1, run 1, rise 1, run 1. Rise 1, run 1, rise 1, run 1. And they're both positive, so I'm going up and to the right. Okay? And then use a ruler to make a nice straight line through those points. And make sure you get arrows on each end. All right, let's graph my next one. I'm going to do this one in green. It's my green equation. My y-intercept is positive 3 because it says a plus 3 right there. I don't know why that's doing that. Plus 3, 1, 2, 3, right there. And then my slope is negative 1 over 1. So I'm going down 1, right 1, down 1, right 1, down 1, right 1. This is nice. We can already see the solution here. Go ahead and draw your line. You want to finish your graph. And we can see that these two lines cross at this point right there. It's at 1. Oh, that looks bad. That point is at 1, 2. Over 1, up 2. So my solution to this equation, kind of your third step here, is to write your solution. And that's the point where they intersect. And this one is 1, 2. So that's the solution to that graph. All right, so we're going to go on to another one. I'm just going to tell you right away that something funny is going to happen on these next two. So we're going to solve this graphically. These are both already in slope-intercept form, which makes it kind of nice. I'm going to graph this one right here in green. So my y-intercept is 5. So I need to go up 5. 1, 2, 3, 4, 5. Put my y-intercept. My slope is negative 3, which I can write as negative 3 over 1. That means rise negative 3, run positive 1. So 1, 2, 3, 1. 1, 2, 3, 1. 1, 2, 3, 1. Go ahead and draw your line through those points. Draw arrows on the end. Should look nice and neat. And now I'm going to graph my other one. I'll do it in blue. So this time my y-intercept is -2. So I go to -2 on my y-axis and put the point for that y-intercept. My slope is the same, -3/1. So I'm going to go down 1, 2, 3 over 1. Remember that you can switch both directions and go up and left if you run out of room. So I can go up 1, 2, 3, left 1, up 1, 2, 3, left 1 as well. Something weird is happening here. If I draw my line through that, I can already see that those lines are parallel, which we already knew, right? Because they have the same slope. So if graphs are parallel, they never meet. And remember, we decided that our solution is when the two graphs meet. These ones never meet. So if your graphs are parallel and they never meet, there is no solution to this system of equations. Ooh, my smartboard is not cooperating right now. There is no solution. That's your answer, no solution. You just have to write it like that. All right, so we've got one more, and I think I made it so something weird happens on this next one too. All right, we're going to solve this system graphically. This one we do need to get them in slope-intercept form still. So let's go ahead and do that. So here's my first equation. I'll do this one in red. I've got 3y minus 2x equals 6. We're trying to get our y by itself. So first, I need to add that 2x term to each side. So I'm left with 3y equals 2x plus 6. I just like to write the x term first because that's how we write it in y equals mx plus b. Then I just need to divide by 3. We're going to have to do the heart method on the right side. So we are left with y equals 2x over 3, or you can write that as 2/3 x plus 6 over 3, which is 2. Let's go ahead and graph that one while it's fresh in our minds. So my y-intercept is 2. I'm going to go up to positive 2. And then my slope is rise 2, run 3, 2/3. So I'm going to rise 2, run 1, 2, 3. And I know I'm going to run out of room if I keep going up 2 over 3, so I'm going to go down 2 and left 3 for another point. We can draw our line through those points. And we are done graphing that one. Let's get our other one graphed here. I'll do this one in blue. So it's negative 12y plus 8x equals negative 24. So again, we're trying to get y by itself here. So I need to subtract 8x. Then I'm left with negative 12y equals negative 8x minus 24. I've got one more step here, and that is to divide by that negative 12 in front of the y. That's the y's coefficient. So we are left with heart method here. We've got negative 8x over negative 12. Well, a negative divided by a negative is positive. And I'm going to go ahead and simplify this. I know that 8 over 12 can be simplified because I can divide them both by 4. So I'm left with 2/3. So this is 2/3 x. And then the other part of my heart, negative 24 over negative 12. Well, negative over negative is positive, and 24 divided by 12 is 2. 12 goes into 24 2 times. Look at these two equations. They're exactly the same, right? If I graph this blue one, it's going to be y-intercept of 2, rise 2, run 3, or down 3, 2, left 3. They look exactly the same. They're right on top of each other. So here's what happens in this situation. If graphs are exactly the same, If graphs are exactly the same, that means they're always intersecting. Remember, we're looking for when they intersect. So if graphs are exactly the same, that means they're always intersecting. And that means there are infinitely many solutions. There are infinite solutions to this. So in every other book I've ever seen, when they write the solution to this, they write, literally, infinitely many solutions. Now, this book's a little different. I think it's important that we go ahead and do it this way. Our book writes it like this. The solution is all sets of x, y such that, and then you just pick one of the equations and write it there. So I'm going to choose the first equation. It was 3y minus 2x equals 6. That was just from the original problem. And that's how we write it. It means all numbers x, y such that we can put them into that equation. As long as they go into that equation, they work because they fall on both the lines. Kind of a funny way to write it, but it means the same thing as infinitely many solutions. So those are your notes for 3.1, translating and solving by graphing, and I believe that's it for 3.1. We're going to do 3.2 in 2 parts, though. All right, come to class with any questions.